Okay, Bridget, I'm doing this in two pieces. I'm actually doing it in a restaurant, so hopefully the background noise isn't a problem here. The first problem is about the sun's radiation. It tells us that the sun is radiating a power that when it reaches the Earth, we get 1.7 times 10 to the 17th watts. Obviously, the sun has an intensity. It's a power per unit area that's coming in, but we will just deal with that. They put it in the power sun to get you thinking like you did about using the Stefan Boltzmann law. So now, if we look at the situations, they said when the power absorbed is 70% of the power of the sun, then the Earth reaches a temperature which is at 253 kelvins. And that says, what would the temperature of the Earth be if the power absorbed was 10% higher? Now, when we think about this, there is one aspect here that is not stated that's really important for us to get straight, and that is for the Earth to have a stable temperature, it must be in equilibrium. Thermal equilibrium means that the rate at which you have heat coming in is the same as the rate at which it's leaving. Otherwise, you're heating up or cooling down. You can't find the temperature if you're heating up or cooling down because it's changing. So what we're going to have in both cases, that is, both the example case that was given and in the original case, the power absorbed is equal to the power radiated by the Earth. And we know that the power radiated by the Earth is equal to the Stefan Boltzmann constant times the Earth's emissivity, which we assume to be the same, multiplied by the area of the Earth that's emitting radiation, and finally times the temperature of the Earth raised to the fourth power. Since this is temperature to the fourth power, we must use units of kelvins. So what we're going to do is say, okay, in scenario 1, power absorbed 1 was equal to 0.70 multiplied by the power of the sun. Power absorbed 2 is equal to 0.80 times the power of the sun. So if I take the ratio of these, I will have my answer. Let me just put in a divider sign here. So we have our ratio. Notice now the powers of the suns will cancel, and I will have the power absorbed 1 over power absorbed 2 is equal to 0.70 over 0.80. There, well, I'm going to leave it at that right now and come up to the equation that I wrote just above in black. I'm going to change to red just for fun here. Power absorbed is the same as power radiated, so that's also going to be the power radiated to over, or 1, excuse me, divided by the power radiated to, and then using that equation finally, sigma epsilon A, temperature of Earth 1 to the fourth power, Earth 2 to the fourth power. Okay, see, we can we can cancel virtually everything in this, as we can cancel that divided by that, and what I'm left with is a reasonably simple equation that says temperature of the Earth 1 over temperature of the Earth 2, all raised to the fourth power, right? Since this was to the fourth, divided by to the fourth, I can just bring the fourth out, is equal to 0.7 over 0.8. I mean, between friends, we can just put 7/8 or 0.875, but I'm going to leave it at 7/8. Well, now we're pretty much done. I want to solve this for temperature 2, Earth 2, so I'll have to take the fourth root, temperature of the Earth 1 over temperature of the Earth 2 is equal to 7/8 to the 1/4 power, and then solving that for temperature of Earth. Temperature Earth 2, excuse me, is equal to temperature Earth 1 divided by 7/8 to the 1/4 power. I could rewrite that more simply as temperature Earth 1 times 8 over 7 to the 1/4 power. And then I just whip out the old calculator. So that's going to be, how's that? Right on top. Excellent. I think I can move it up there. Yeah. Well, it's going to be equal to 253 kelvins multiplied by 8/7 raised to the 1/4. Let's see if that came out. Nope. It's easiest just to delete it and start over. 253 times 8 divided by 7 raised to, how about this? That was excellent. Deleting is my nemesis here. Raised to the 0.25 power. That's 1/4. Oh, you're kidding me. 8/7 raised to the 0.25. Not to the 25. Are you? There we go. Okay. So I got that, and now I just multiply that by my 253. Boy, I hope it was 253 at this point. And so I have 261.6 kelvins. Now, let me make sure that was the right temperature. 253. I think that's what I put in. And of course, 261.6 kelvins is about 8.6 kelvins higher. So that's how much the temperature would increase